Let's look at a few examples so we can figure out where a function is concave up and concave down. So let's look at the function f of x equals x to the fourth minus 4x cubed plus 5. We want to describe the shape and the turning points of the function. So to help as we work through this, knowing what the graph actually looks like will, I think, give us a little bit of encouragement here. So let's start with finding the derivative. F prime of x is equal to 4x cubed minus 12x squared. We'll set that equal to 0, and this will give us all the stationary points. So I can factor out a 4x to the second, and that leaves me with an x minus 3. So x equals 0 and x equals 3 are stationary points. Okay, let's make a sign chart for this. X equals 0, x equals 3, values of x, values of f prime. All right, let's get an arrow and see what I'm looking at. All right, so let's find out what happens from negative infinity to 0. Pick a number less than 0. How about negative 1? Plug it into the derivative. I'll plug it into the factored form. Doesn't matter what x is, this is always going to wind up being a positive value, multiplied by whatever this is. So if I plug in a negative 1 here, this is going to be a negative. Positive times a negative is a negative. Okay, let's pick a number between 0 and 3, like 1. If I plug in a 1 here, I'm going to get a negative times positive. Still gives me another negative. And then finally, if I pick a number greater than 3, like 4, and plug it in, I'll get positive times positive is positive. So this tells me that my function is decreasing, it levels off, and then is decreasing again until I get to 3, which means I'm going to have a local minimum, and that's what's happening. We're decreasing, it levels off at x equals 0, decreases some more until x equals 3, then I have a local minimum there, and then it's increasing till infinity. So that's the information I got about what's happening here. Now I am going to write, let's make a note, that we have a local minimum at x equals 3. And we can plug 3 into the function to see what the y value is. All right, now let's look, to figure out concavity, let's look at f double prime. So the second derivative will be 12x squared minus 24x. We'll set that equal to 0. We can factor out a 12x, and we're left with x minus 2. So we have zeros at x equal 0 and 2. Once again, we'll make a plus minus chart. Actually, let me line this up with the other one best as I can. Here's 0, and then x equals 2. These are the x values. Now remember, it's important to label your chart so we know we're looking at f double prime here. And we know f double prime is 0 there and there. So let's pick some other values. So when x is less than, how about negative 1? If I plug it into f double prime, I'll plug it in here, I'm going to get a negative and another negative. Negative times a negative is a positive. So this is telling me that from negative infinity to 0, my function f is concave up because its second derivative is positive. All right, let's pick something between 0 and 2. How about 1.9856? When I plug that in here, I'm going to get a positive times a negative is a negative. So we know my function f is concave down between 0 and 2. And then if we pick a number greater than 2, like 3, and plug it in here, we're going to get a positive times a positive is a positive. So that tells me that, let's switch to blue, that my function f is concave up here, it's concave down on this interval, and then it's concave up there. So if we want to write this as inequalities, we can say concave up when x is less than or equal to 0, and when x is greater than or equal to 2. And it's concave down when x is between 0 and 2. And so that describes the shape and the turning points of our function. Not so bad. Understanding the concept, conceptually putting all this together, is the tough part. The math involved is not very tough. Finding a first and second derivative, factoring, setting it equal to 0, the sign charts. That's not really difficult. It's putting it all together, and I think looking at the picture then you can see this is exactly what we found out. At 0 it levels off, it's concave, it's decreasing, it's concave down. At 0 it levels off, and then it changes, it's concave up, F, let's start this again. F is decreasing and concave up. And when we get to 0, now it's still decreasing, but now it's concave down until we get right here. And then it's still decreasing, but now it switches to concave up, has a local minimum at 3, and then is increasing and concave up after that. All right, let's look at another example. Consider this function. A nice polynomial again. So let's break this into separate questions. First, let's find and classify all the points where the first derivative is 0, i.e. the stationary points. So f prime of x is 12x cubed minus 48x squared plus 48x. We're going to set that equal to 0. We can factor out at 12x, and we're left with x squared minus 4x plus 4. We can further factor that. 12x times x minus 2 times x minus 2, or x minus 2 squared. So that tells me that my stationary points are at x equals 0 and x equal 2. Let's make a sign chart for this. X equals 0, x equals 2, and we're looking at f prime. It's 0 at those two spots. Okay, we're going to pick a number less than 0, like -1, plug it in here. This quantity, since we're squaring it, is always positive. So basically plugging in -1 there, we're going to get a negative times a positive is a negative. If I plug in 1, I'm going to get positive. If I plug in 3, I'm going to get positive. All right, so this is telling us that since f prime is negative, f is decreasing, levels off, increasing, levels off, continues to increase. So it's leveling off here. That's not a local min or max. Here we have a local minimum because I know f is decreasing. So let's put f here, and we have a local minimum there. And then this is just a stationary point, not a local min or max. All right, find the intervals where f is increasing and decreasing. So we just look at our sign chart, and f is increasing when f prime is positive, so that's 0 to infinity. So that's when x is greater than or equal to 0. And it's decreasing when x is less than or equal to 0. And of course you can write that with interval notation as well. Okay, let's continue on. Finding classifiable points of inflection. So now we need to look at f double prime. So let's take the derivative of f prime. We're going to get 36x squared minus 96x plus 48. We'll set this equal to 0. We can factor out a 12, and we have 3x squared minus 8x plus 4. And we can factor that, I think. We've got a 3x and a 1x. And then let's try a 2 and a 2. Both have to be negative. That's a 2x and a 6x is 8x. Check. So we've got inflection points here possibly at x equals 2/3 and x equals 2. Now notice, at x equals 2, we know the first derivative is 0. That was a stationary point. All right, let's make our sign chart for this. So I'll put it over here. So we have at 2/3 and at 2. This is x. And remember now we're looking at f double prime. It's 0 at those two spots. So let's pick a number smaller than 2/3. I don't know, how about 1/3? If I plug it in here, this is going to be a negative quantity. This will be a negative quantity. Negative times a negative is a positive. So f double prime is going to be positive on that interval. Okay, let's pick a number from 2/3 to 2. How about 1? That's a negative, that's a positive. We're going to get a negative on that interval. And then if I pick a number greater than 2, I'm going to get everything positive. So notice what's happening here. Since f double prime is changing signs at 2/3, and then it's changing signs again at 2, these are both stationary points. Now, since at x equals 2, the first derivative is also 0, this is a stationary inflection point, and this is a non-stationary inflection point. So when it says find and classify all the points of inflection, we're going to write exactly that. So, and if we can plug them into the function to get the y values, but at 2/3, the function value is about -2.5, and that's a non-stationary inflection point. And then when x equals 2, f of 2 is equal to 7, I believe, and that would be a stationary inflection point. And all that means, a stationary inflection point, it just means the tangent line is horizontal at that point. It's a stationary point, and the tangent line is horizontal, like y equals x cubed at x equals 0. That's a stationary inflection point. All right, and then finally, find the intervals where f is concave up and concave down. We've got that from our sign chart. So we're going to say concave up. And that would be when x is less than or equal to 2/3. And also when x is greater than 2, greater than or equal to 2. And then it's concave down in between those two. So when x is between 2/3 and 2. And that's it. So like I say, the mathematics is not very difficult. Putting it all together and understanding the connections between the three functions, f prime, f double prime, is important. All right, I'm going to do one last example for you. I'll work through this a little more quickly. Let's look at a function that's a little bit different, not a polynomial. Find the x intercepts, if there's more than one, and then y intercepts. Well, let's start with the y-intercept, because that's usually easier. We set x equal to 0. So y is equal to 2 minus e to the 0, which is 1. So that's just y equal 1. For the x-intercept, we're going to set y equal to 0. So we have 0 equals 2 minus e to the negative x, or e to the negative x equals 2. And so we could say negative x is equal to the natural log of 2, converting that to a log. And so x is equal to negative natural log of 2. So some negative decimal number. And those are our intercepts. Find the intervals where y is increasing and decreasing. So we're talking about the function y. Increasing, decreasing means we need to look at y prime. So y prime the derivative of 2 is 0, so we have negative e to the negative x, and then the chain rule times the derivative of negative x, which is negative 1. So we have y prime is equal to positive e to the negative x. By the way, that's the same as 1 over e to the x. Now 1 over e to the x, no matter what you plug in for x, remember what e looks like. The function e looks like this. The domain is all real numbers. This is just y equal e to the x. And the range is all positive values, greater than 0. So that tells me that, let's draw an arrow here. No matter what I plug in for x, this is always going to be positive, and then 1 over positive will always be positive. So y prime is always going to be greater than 0, since 1 over e to the x is greater than 0 for all x. Y prime is greater than 0, always. So that means that y is increasing everywhere. If I can fit that in. Okay. So we didn't even have to make a sign chart for that. Find the intervals where y is concave up, concave down. So same idea, this time concavity, we look at y double prime. And so the derivative of e to the negative x is negative e to the negative x, which is the same as negative 1 over e to the x. And by similar reasoning, that's always going to be, that's always going to be a negative value, because 1 over e to the x is always positive. So that's always going to be less than 0. Therefore, y is always concave down. And so we didn't even have to make a sign chart for that as well. And then lastly, explain why y equal 2 is a horizontal asymptote. So for horizontal asymptotes, we need to look at what happens as x gets really big or really small. So our original function was y equal 2 minus e to the negative x. So what happens as, let me write this a different way, 2 minus 1 over e to the x. So what happens as x approaches positive infinity? Well, as x gets really, really big, e to the x gets really, really big, and 1 over e to the x therefore would get really small and closer to 0, and then 2 minus a really small number is going to give us numbers that are getting closer and closer to 2, a little bit less than 2, but getting closer and closer to 2. So as x approaches infinity, oops, change colors there. As x approaches infinity, 2 minus e to, I'll just write y instead of writing that, be more succinct. As x approaches infinity, y is approaching 2 from below. But it'll never actually equal 2. We're always taking smaller and smaller amounts from 2, which 1.9, 1.99, 1.9999, etc. So that's why we have a horizontal asymptote. Now what happens, by the way, as x approaches negative infinity? Well, as x approaches negative infinity, then e to the, use my arrow, e to a really big negative number, like I can actually, let's look back at this form, would be easier. Put in a negative number for x, like negative 100. This becomes e to the positive 100, which is a really big number. 2 minus that is going to give me a really big negative number. If I plug in negative 1,000, this becomes e to the positive 1,000, which is even bigger. 2 minus that is an even bigger negative number. So as x approaches negative infinity, y is also approaching negative infinity. So there's no horizontal asymptote as x goes further out to the left. The function is going down farther and farther and farther. Okay, so that's it. So the problem set, come from sections 13E and 13F.